So, good afternoon, and thanks for coming. I'm Alessandro Negro, and as Miguel said, I'm the chief scientist of GraphAware. And in this presentation, I'm going to be talking about the role of graphs in the machine learning panorama. More in detail, we will see how graphs can be used in different ways in your machine learning project. And under several perspectives in terms of algorithms, in terms of data sources, in terms of models. And this is, or at least pretend to be, a really practical presentation in which we will go through concrete use cases, and we will see a lot of example models, and we will even examine different type of architectures and end-to-end framework. But before start, I would like to point out how much important is this new trend in the artificial intelligence panorama. And I would like to do so using other words from other people. For example, the founder and CEO of Lumiata, that is a company that provides that helps healthcare organizations to make prediction, firmly believes that there is it's at the intersection between graphs and machine learning that the next evolution lies, and where new companies are emerging and will emerge in the next years. And on the other side, the chief technologist of DataStax, that is in this case a company providing a big data platform, and recently they added even support for graphs. He's abstained that there are a variety of use cases in which graph database is a better fit than other technologies like relational database and even other NoSQL database. And he lists, for example, master data management, recommendation engine, customization, fraud detection, and together with IoT and classical networking. And last but not least, Jim Weber, that is the chief scientist of Neo4j that you obviously know, said that a machine learning algorithm could help data scientists to discover meaning from the data. And on the other side, graph databases enable efficient data storage and navigation of this data. So graphs could be at the beginning and at the end of a machine learning process. And this is a really interesting sentence, because this is from where we move, and we will move along this presentation in order to show how graphs could be really pervasive in a machine learning process. So, just a few words about machine learning. Machine learning is not a new concept, because in the 1959, Arthur Samuel said that machine learning is the field of the study that gives computer the capability to learn without being explicitly programmed. In other words, we can say that machine learning is the science, or under some perspective, even the art of programming computers so that they can learn from data. And this is a really interesting phrase, because apart from learning, that is clear from the name, it's clear that this happened from data. Even if you have the best algorithm in the world for providing recommendation or providing any type of machine learning, and you start from wrong data, at the end, you will get wrong results. So let's consider a classical, and maybe the most simple workflow in machine learning. Obviously, everything starts from the problem that you could have. That could be, for example, customer segmentation, or recommendation, fraud detection, or whatever else. So starting from the problem, analyze the problem, and find a list of algorithms that could, in some way, help you with the problem. At this point, choosing the list of algorithms, you need to train them, and at that point, evaluate the results and decide if it could be the case to launch your application, or just go back, reanalyze the problem, and choose other algorithms, or obviously changing the training data. So this is the most simple approach. But let's say 80% of algorithms in the machine learning panorama has something called model, that is the result of the training process. The issue here in this other schema is that obviously this phase, the training phase, could last for a lot of times. That could be hours, days, months, accordingly to the type of algorithm that you have and the amount of data that you have. But this could be fine for some use cases, but in other use cases, what could happen is that you cannot, in some way, feel the behavior, the changing in the behavior of the user, for example. So another possible workflow in this case is when you have this continuous loop in which you continuously update your training data and through this training update your model so that you can follow the changes in your environment, in your context. So starting from this simplified workflow, we can define three main areas of challenges about machine learning. The first is, as I said, the data. Because in order to get good results, you need to have good data. Good data means, first of all, that you have to have enough data to be processed in order to get good results. But obviously, what is important is that you have even good quality, good data quality. That means because you can have different issues about this. For example, you don't have enough data. The set of features that are available are not the right one. Or, for example, you could have not representative data, for example. And a way for solving generally this issue is, to managing different data sources. But again, this could be a problem in some way because you need to merge data coming from several data sources. The second area of issues is the algorithms. Obviously, you need to have good results. This is clear. But when you consider the algorithm, you need also to take into account, for example, the computational efficiency of this graph in terms of memory, in terms of time, in terms of CPU, and so on. Because obviously, you would like to get results as soon as possible, not after months or later. And another issue is obviously that not all the algorithms allow you to continuously update your model. Some of them just require to start from scratch. And so that means that you cannot provide some sort of real-time updating in your model. And finally, as I said, in the 80% of the cases in which you have a model that is the output of your training phase, you have to store this model in a way in which you can easily access to it and provide final services to your user. That will be a recommendation, that will be some sort of clustering or some sort of classification. So this is important to store in the right way, and this could be even huge in terms of the amount of data that we have to store and access them in the fastest way possible. So on the other side, we have graph. Graph, to be honest, is a very, very simple concept because it's a mathematical concept that can be just represented as a set of vertex and a set of relationship between them. And you can just say if it is direct or indirect, but at the end is just this. Obviously, this is not enough in the computer science because you would like to have more information about nodes, more information about the relationship. So usually, the graph database providers add some little bit of love in the graph, adding properties, for example, that can be related to nodes or to relationship, add labels that can be used for defining, for example, for typing nodes or relationship. And so you can easily enrich the amount of knowledge that you have about every single node or every single relationship with this set of properties. And this is how, for example, Neo4j provide graphs as a so-called property graph. But what is important is that along this presentation, we will see how graphs could be really useful for machine learning. But this means also that you would like to use graphs as they are. And it is a big difference between the several database providers, because there are providers like Neo4j, for example, that they use to store in a way in which they define a native graph. So that means that mainly they store graph as a set of nodes, certain relationship, and this means that you can easily navigate this graph as it is. Other, like, for example, DataStax, used to store graph as a key value. So at the end, the graph is no more than a sort of wrapper or graph representation of a key value data store. And in this case, it's true that you can store a lot of data, and you can also perform some shard, but at the end, you cannot navigate the data as they are, as graph. Starting from this, obviously, you can have a huge graph that you would like to analyze and check. So machine learning at the end, enables computer system to solve complex real-world problems. And recently, machine learning and more in detail deep learning models demonstrate high predictive capability when trained, again, on a huge amount of data. Labeled or unlabeled is accordingly to the type of machine learning algorithm that you would like to use. So in this scenario, graph-based machine learning is becoming a very important trend because a lot of companies are also using this type of approach for providing support, let's say, to the machine learning infrastructure. And let me just cite Google, for example, that recently introduced this concept of knowledge graph for providing advanced search, what they call the relevant search. Or, for example, they have a project called Google Expander that allow you to have automatic response to email, for example. And they use this huge knowledge graph to solve the sparsity problem and to have more data to be processed during their machine learning phase. So at the end, we can say that using graph, we will see later, as a basic representation for data could be really useful in the machine learning process and has a lot of advantages. As before, let's consider three main aspects of a machine learning workflow, and we will see how graphs could be helpful in all of them. First of all, as a data store for the data sources. In this case, we will see how we can model interesting stuff like tensors, for example, but also we will see how we can gather data from several data sources and have this sort of huge knowledge graph that we can use as a starting point for our machine learning process. And we will also see some possible architectures that allow you to store this huge amount of data and process this huge amount of data as a starting point for the further phases. Then we will see some algorithms that are effectively graph theoretical algorithms that can be really useful in a lot of machine learning tasks. In particular, we will see some example with natural language processing, and not only, and even a recommendation engine. And finally, we will see how we can store several models in the form of a graph. So when you think about a machine learning process, you can have two different approaches, let's say. On one side, you could have the data scientist approach, in which you can say, OK, which algorithm I will use for my machine learning process, and this is cool, and this is correct. But when I think about a machine learning process, the first thing that I have in mind is, OK, what will be the data flow that I can create in order to have data coming from the several data sources, store them somewhere, and start processing them, and then provide effectively services to the end user. And this is not a side problem, because you have to think about this since the beginning, because without this, you cannot provide any type of services to your end user, even if you have the best algorithm in the world. So about this, this is a really interesting type of architecture that was famous maybe a couple of years ago, when Nathan Mars introduced this three-layered base architecture that is a scalable and fault-tolerant processing architecture just designed for fast streaming of data. He created, as I said, this is invented, let's say, these three layers, where we have batch layer, serving layer, or service layer, and speed layer. The idea is that once data coming from several data sources, they have to be stored mainly in this master data set. And there is a concept here that is really important. What he said is that facts are just, events are just facts. They are as they are. They cannot be changed. They happened. So the idea is that once you think about this master data set, you should think of it as a repository of facts that cannot change over time. So even if you would like to have a complex machine learning algorithm, you should always start from storing facts, because they cannot change. If, for example, I'm monitoring calls, for example, they happened. So if I called Michael, it happened. So at that time, it lasts for 3 minutes, and that's all. This cannot change over time. This is true. So the idea is to store in the batch layer the events as they are, without any type of changes. And since they could be a lot, he suggested to store, for example, in HDFS or this type of data set where you cannot access in a random way or whatever else, because you don't have to access directly here. Because The service layer is a sort of list of views, materialized views, we can define them in this way, on the master dataset that are designed accordingly to the specific use case that you have. But since you could need time for migrating data from the master dataset to the batch views, what happened is that he introduced this layer that is just a layer that stores part of the data for cover the time required for feeding these batch views. So that when you perform query here, you can have the most part from here and just the real-time data from here so that you can have a complete access on the entire data set in real time without having to, wait for ages. In this sense, where is the graph? The graph is here, for example, or can in an intermediate layer here, because you can have a sort of views that is a graph views of your data. And I will give you an example. Supposing that you would like to monitor some subjects for any specific reason, could be your wife or a terrorist, and you would like to, in some way, predict where they will be in the next few hours or in the next days. So let's start again from the facts. In this case, we have these data that are there. I'm referring to this interesting paper where they starting from the cellular tower data that are mainly data like this, where you have device ID and a lot of events related to connection, disconnection, or whatever else type of events that are connected to the fact that the phone is, physically connected to the tower. And in reality, they use also other information because for their experiment, they installed a spy app on the phone of subjects that in this case, they were aware of this experiment, where every 10 seconds, this spy app sends information about the time and the list of the 4 topmost several towers to which the phone is connected with the related strength. Starting from this set of data, and again, I would like to stress on the fact that these are simple facts, so cannot change, they created these views. That is a graph where they have these nodes that are cellular towers, and the relationship here is related to the fact that they co-occur in the same message. As I said, this means that at that time, the phone was connected to both these towers, for example. And the strength, the weight of this relationship is the amount of time, or the part of amount of time across all the time in which it was physically connected. So this is a graph for a specific subject. Then they have a graph like this that is for all the subjects, obviously. So what they did? So they created, they tested 3 different types of clustering algorithm: NCAT, Q-modularity, that is a specific type of community detection system, and threshold groups for creating, different clusters that mainly represent area in which a user used to be. Then, what is interesting is that after this, they created a dynamic Bayesian model for predicting, starting from this cluster, how the user will be in the next hours or in the next days. And it's really interesting because they introduced also the concept, some variable like if it is a working day or is a weekend day, and so on and so forth. So what is the takeaway from this example? Is that in this case, starting from a concrete problem, that is, I would like to monitor these people and predict where they will be in the next few hours, you can create an architecture like the Lambda architecture where you have the list, the data that are just in the master data set. Then you can create several views like this. In this case, is a graph, for example. Then you can start having some machine learning like clustering algorithms that allow you to create these clusters. And on top of this, again, apply another machine learning tool that allow you to create a predictive model that allow you, having this speedy layer that say, OK, the user is here, to say, OK, it will be in the next few hours there or that. So this is the idea. So another approach, maybe simpler than before, is, for example, related to the recommendation engine. We can simplify the recommendation engine as a function from, that starts from a matrix, a user item matrix, and create this relevance score. So in this case, I can store the data source with a bipartite graph. It is really simple, where you have users here and items here. It is really simple. And the action between them is represented by this labeled relationship between users and items. So in this case, why storing data in this way is really useful? It's useful because, you know, if you would like to apply the classical collaborative filtering approach, that is the KNN, you know that you have to compute similarities between this item and all the other items, or between this user and all the other users. And this is true for all the users and all the items. But if you have this representation, for example, you can find easily that if I would like to compute similarity between this item and all the other, I can avoid to compute this, because since it is connected only to this user, when I create my vector for this item, it will not match with none of the other. So at the end, the similarity between this and all the other will be 0. So I don't have to compute this. And it's the same for the other use case. For example, if I would like to compute similarities for this, I have to compute only the similarity between this and this. And this is a great optimization in my algorithm, because I don't have to just have a computation between this and all, but I can use a simple query to refine my algorithm in order to avoid to make useless computation. And this will improve the quality of my final algorithm, because I reduce the time for computing similarities. But things here become more interesting, because supposing that you would like to create an advanced version of recommendation engine, the so-called context-aware recommendation engine, where you have an application like this. Supposing that you would like to implement an application for recommending films from the app, films that will be transmitted in a cinema, so not on Netflix or whatever else. So obviously, if I will implement an application like this, I will take into account the context, because the context really matters. For example, in my case, I like to see a film like, I don't know, action movie or horror movie or, science movie, if I'm alone. If I'm with my wife, for example, we prefer to see dramatic film or, comedy. Or if I'm with my kids, I like to see cartoons or family films. So obviously, the company that I have, when I try to get a recommendation, could affect a lot the recommendation itself. So here is a way in which I can represent the context. In this case, it's a very, very simple context that affects my, you know what I'm talking about. About the context in which I am when I would like to, to get the recommendation. So in this case, the function is more complicated, because instead of acting on a simple matrix, I have a multidimensional array that is a tensor. So, and let's say that storing tensor is a really complicated task, because you could suffer of the issue of the sparsity of the data. So even in this case, using graph could be a really good help, because in this case, I can have these elements and all these indices for the tensor. And what is nice is that the amount of memory necessary for storing these tensors is really the minimum necessary for it. I cannot store, I think, in less than this, a complex tensor like this. But more than that, accessing to this tensor is easy, because I can operate slicing, for example, in a really easy way. Just because I can fix two of them and then slicing. It's really easy. But even easier is, for example, adding new indexes to my tensor, because I can add a new node here, connect to this, and that's all. I don't have to change the entire structure of the tensor just because I would like to add a new index. So in order to complete this overview on how to use graphs for data sources, I would like to introduce this, the knowledge graph. Mainly, the idea here is really simple. I would like to gather data coming from different data sources and converge them in a single, highly connected source of truth that I can use then for whichever type of algorithm or machine learning or purpose I want. This is an example of an architecture that we built for a company here in the Emirates. That is a company that provides, e-commerce site mainly. So the idea here is that we gather data coming from, I don't know, clickstream, data, content providers, or, for example, warehouse or sellers, and so on, and merge all these data in a single knowledge graph so that we can connect dots in a way in which we can have a lot of information related to every single product. For example, we can have detail about the description, so the list of features. We can have detail about the availability in the warehouse, and so on. And starting from this, we applied a lot of machine learning techniques like recommendation engine, faceting extraction, grouping, clustering, and so on and so forth. And in this case, we store these models, this information that are created starting from the initial knowledge graph, again in the knowledge graph itself, increasing the amount of knowledge that we have about the data set. And in this case, we also store a lot of views in Elasticsearch just to avoid to hit too much on the graph database that is dedicated to the other stuff. But obviously, when needed, we have the API connected directly to the graph. So let's move forward and consider how important could be the graphs, the graph algorithm, in order to help your machine learning task. We already saw an example before when we have this clustering algorithm that could help to define, to group stuff together and then apply a dynamic model on top of it. But these are a list of really, let's say, basic or well-known algorithms that are graph theoretical algorithms that have a lot of uses in the machine learning panorama. Let me give you some examples. We will see an example later based on PageRank that is a special case of random walk. But for example, in the case of graph matching can be used that allow you, just to say, to compare graph and find similarities between them. You can use graph matching, for example, to process of ontology extraction or for questioning answering system. You can use the shortest path for computing a semantic distance in a semantic network. You can use a minimum spanning tree for extracting taxonomies from text. And there is also this very, very new, let's define it, graph theoretical algorithm that allow you to define, to extract a vector from graph, mainly. And using this vector, you can perform a lot of analysis on the graph itself. And for example, there are some trend that use this not-to-vec for computing recommendation, for example. And they show a great performance, both in terms of times and in terms of quality. So I talk about PageRank. Let's see how, for example, PageRank can be used in a natural language processing process. So supposing that you would like to implement a tool that automatically extracts keywords from text. So the idea is that you have a document and you would like to find the most important keywords that in some way describe the text itself. There is this interesting article in which they use this approach. They extracted from the document all these tags. Obviously, they are filtered based on the length, based on the stop word list, and so on and so forth, and then create these relationships. These relationships are created in different ways. They propose several. The most effective one is when you consider the co-occurrence window. So you have n-grams, that could be 2, 3, or 4 n-grams. And then you have this relationship if these two words occur in the same n-grams. So if you have a window of true, for example, they are just one after the other, and so on. So once you created this graph, what they did is to perform a PageRank algorithm on top of this in order to find the most interesting words in the text. And then they try to merge them to create a multi-words keyword. At the end, the results are really amazing because they compared their result, that is this line mainly, with the result obtained by another algorithm that is supervised. Because the great power of this approach is that it is completely unsupervised. That means you can give the text to the system, and you will get back the keywords. And in this test, they compared the keywords extracted automatically with the keywords extracted manually by people just saying, OK, these are the list of keywords for this document. And the results are really interesting because they overcome the other results based on supervised algorithm. So And that was a good example in which, I mean, we have a simple graph-based algorithm that helps to get interesting results in other fields of machine learning, like natural language processing, for example. So to conclude this, overview on how to use graph, the last part is how to store models that are, at the end of the machine learning process. Again, we already saw a lot of them. Some of them are really simple, others are maybe more less obviously, but all of them are really interesting. Let me give you some example. We already talked about, for example, key nearest neighbor. In this case, the model is no more than a relationship between two items. What is interesting in this approach is that you can store easily more than one similarity between items. That could be, for example, cosine similarity, Tonimoto, Yakkard, Euclidean, or whatever else. Or, for example, you can store k and n similarities together with content-based similarities. And then you can easily create a hybrid recommendation engine that easily combine similarities in order to provide recommendation. And once you have this type of model here, you can easily access to it and get funny stuff like, for example, if you like to see, I'm seeing Iron Man 3. What is the most similar movie? It's simple, just a matter of a very simple query that in less than a few milliseconds can reply to you. So navigating the model in this case is really, really simple. And this means that you can get easily results for the user in a matter of milliseconds. Another example is the famous Markov chain. As you know, a Markov process is mainly states and probabilities where the probability in the transition is just related to the current state, so there is no memory in this case. So storing a Markov chain in a graph is just a matter of nothing. You have just nodes that represent states and relationship with their weight that represent the probability of the transition between this state and the other state. And obviously, the sum of the weight of the outgoing relationship is 1, just this. And the last one is a decision tree. Again, S3 is no more than a special type of graph. And obviously, you can also store a random forest that is a set of trees. So before talking about concrete application, just some examples about our experience in building this type of machine learning on top of graphs application, I would like to point out how what we saw today obviously doesn't mean that you have to use a graph everywhere. Obviously, you need to choose the right tool for the right job. That means that you could find that could be useful to store only the model in the graph. For example, in some of our previous experience, we used to build the k and n outside of graph and then store in the graph only the similarities, for example. In this case, we can use other tools like Spark with Mahout, for example, for computing distances, and then store only the results in the graph. And at that point, since we had a lot of data that we don't want to store in the graph, it appeared to be the best solution, for example. So this is just to let you think about the best approach that is not just using graph for everything. Just decide when it's necessary and when it is not necessary. So now, let's go through a couple of examples of real application that we developed using what we said today. So a good example in this direction is natural language processing. First of all, because it is the current main effort in our R&D, and also because natural language processing application find efficient solution within graph theoretical framework. Let's say that this is not a new idea, because even Freud, at the beginning of the last century, sustained as networks and graph could be a good representation for language units and the relationship between them. This is true because we usually tend to define text as unstructured data, but this is not true, because language has a lot of constraint, a lot of structure related to the grammar, related to the rules, related to the best practice. So when you start processing text with tools like Stanford NLP or OpenNLP and extract tags, sentences, and typed dependencies, as well as core F, all of them can be easily stored in a graph because you can easily store tags as node and relationship between them using a graph. So we can say that a suitable graph model for natural language processing is for sure a graph because allow you to easily extend it also, adding, for example, an ontology on top of a single tag, adding the related concept, and so on. So starting from this idea, we developed what we call the GraphAware Natural Language Processing Framework that is, or I'm to be, an end-to-end framework that offers from low to high level a set of functionalities, services, and even application that, as I said, use a graph as a main data storage model and extract the process phase using Apache Spark as a distributed platform for EV computation, and also integrate a lot of other software and hardware for easily allow user to integrate this tool with their own interface, for example, their own infrastructure. For example, we deploy integration with Elasticsearch, with Neo4j itself, but also with Amazon Alexa, for example, and other tools like this. Since the beginning, it appeared to be a really complex task. So what we did is to design this type of architecture that we called graph-centric clockwise architecture. Obviously, the term graph-centric is related to the fact that we had and we have the graph at the center of this architecture, where every single module just read data from the graph, process it, and store data in the graph. In this way, since the graph is a NoSQL database, so can be easily extended with the new relationships and with new nodes. We can keep, these modules loosely coupled between them because we can just agree on for every single module we can agree on the type of data that are here and the type of data that will be produced. That's all, because this will read data again and process in the way in which you want and store new data. If, for some reason, some of this module would like to extend the graph schema, it could, without any type of problem, because this will not affect in any way all the other, obviously. It's supposed that will not delete other type of nodes. It's clear. While the clockwise term is related to the fact that when you think about natural language processing, you have to think about a sequence of steps that you need to be careful before, the next one and before the next one, and so on and so forth. So again, in this case, the graph-based representation helps us not only in terms of having powerful tools like PageRanks, like other algorithms, but also because in terms of architecture, helped us a lot for clipping this loose coupling between modules. And to conclude, I cannot not talk about recommendation, obviously. That is our classic in some way. So to be honest, we already talked about all of this stuff. This is just a recap about what we already said. So in the case of recommendation engine, you can use graph for a lot of stuff. Obviously, storing the data sources in this case, because you can use bipartite graph of tensors. And we already saw why this could be useful. We can use this co-occurrence, as I said, in order to speed up the KNN process. Or you can use this new technology that is Node2Vec to create a quite new recommendation engine. And you can store these models in different ways in the graph. So in conclusion, what is the takeaway about from this presentation? First of all, you should think bigger. When you think about machine learning, you cannot be focused on simply on the algorithms or on the specific detail about the machine learning training process, but you need to think about the entire data flow, the entire workflow that you have to build, starting from the how to ingest data into your machine learning engine up to, how to provide effectively services to the end user. Otherwise, you cannot think about machine learning at all, because even, as I said, with the best algorithm, you cannot provide effective service to your user. And obviously, in this, I hope that I showed how graphs could be helpful. And but as I said, when you think about your architecture, you need to think about what could be the right infrastructure, the right algorithm, the right graphs, the right models for your specific use case, because there is no one solution fit all. Obviously, all the algorithms, all the architecture require their own approach. And at the end, think about us. As you saw, we had really a lot of experience in the direction because we helped a lot of companies building this type of stuff. So we gained a lot of expertise in this direction in terms of combining machine learning algorithm with graphs and providing at the end production service to the customers. That's all. Thanks for your attention. Any question?
What about the NLP you talked about? Can you give an example maybe of a specific project without getting into any names or too much details about what you're doing in that space or something interesting you're doing? So, recommendation engine, that's clear, but I'm kind of more curious about NLP.
We started working with natural language processing because we had an interesting prospect, an interesting customer, some maybe 1 year ago, a little bit more, where they were interested in processing blog posts and other type of textual data in order to create a sort of recommendation engine for suggesting a place where someone could go and live for some reason, for example, or some helping charity somewhere in order to help, because the project was aimed to help people with some issues in some way, drug or veterans or this type of stuff that have social issues, and so they need help from the government, for example. And then they were creating this sort of a portal where people just could describe their own needs or describe their own condition, and other people just describing how they got helped in some way for their specific needs. And so they have this platform where they should, matchmaking the offers with the needs in terms of getting the best place where go and live or get some help or this type of stuff. But in general, let's say that starting from this first project, we noticed that having graphs could help a lot in terms of the capability of creating, for example, knowledge graph, where you can, as I said, really merge data coming from blog posts, for example, from click streams, from ontology data sets, in order to have this huge set of data that you can navigate in the way in which you want, and get at the end a lot of insight from the data that you don't have at the beginning, applying a lot of machine learning techniques. For example, recently we are working to this new platform that is that we call the GraphAware knowledge platform, where the idea is simply, if you can define it so, to aggregate all this data, process this data, and even extend from several data sources that allow us to get more insight about the data. And then at the end, get a tool that could help people make a decision, that could in some way help people to decide in a way which cannot be done before. I will give you an example. We had the prospect in which we have this company that would like to help companies to merge. When you have big companies and you would like to help in the merging process, the issue is that each of them could have a lot of contracts with other providers. And it could happen that when you perform the merge, these contracts could be in contrast because you have a simply different agreement with them. So if you talk about huge companies, they could have a lot of documents to be analyzed. So in that case, the idea is that having a platform like the GraphAware knowledge platform could help you because it help you to navigate easily the documents, the huge set of documents that you have, and, for example, help you to discover issues that otherwise will be impossible to discover. Another example is, for example, if you have a lot of documents and you would like to access them in the fastest way possible because in the case of NASA, for example, they would like to access to this data set as soon as they have an issue. They have this huge data set where they have they call lesson learned data set, where they have what they learned in 50 years of NASA. And they would like to access this data set as soon as they have an issue with a space shuttle that is crashing somewhere and say, okay, what happened in the 1950 in the same way? What we did at that point? It's really complicated to do this in this huge set of data. So the idea is that having this platform, you can easily search by keywords, search by topics, search by, some navigational path, even mental navigational path. And this allow you to easily access to what you need in the fastest way, for example. So when you talk about NLP and graphs, there are, I have in my mind a lot of examples in which we had a lot of conversation with people that really needs this type of platform for managing this huge set of documents that are somewhere and that cannot be used. The last one. At the Rexis conference that was at the end of August, for example, a new effective trend is that there are a lot of companies like Trivago, for example, or Skyscanner or Booking that currently have a lot of data that are completely unused, that are related to the reviews of the user. So they have all these reviews of the user, and they cannot use them because they cannot simply extract knowledge from the reviews until now. And so they are using natural language processing in order to extract knowledge from these reviews. And so instead of having a simple 5 stars system that describe if this hotel is good or not, they can extract, an effective evaluation of that specific hotel in terms of staff, in terms of cleaning, in terms of restaurant, in terms of location, from the reviews, not from the click on the star on the site. And it is really powerful because they, at the end, they gained a lot of knowledge that they already have, but they cannot use, just using natural language processing, for example. That's all.
Thank you, please. We had one case like doing an investigation for emails in one company, and we had a struggle as a small company. We don't want to consult Big Four or consultancy because these, for multiple reasons, like for confidentiality of information and to able to detect like all the emails between people. And how, then finally we get to know like a graph theory can help us in extracting information from people, the relationship between people, the strength between people. But the thing is also it was like a couple of years back, it was difficult. Like these tools were not that easy to finding relationship because the easiest way is the intent. Like someone will tell us, oh, in that date, this is the, to open an investigation with someone is unhappy from something and he will tell us. Then we open an investigation. But how is it easier now to do these things from email databases? Because this is one of the things that I feel could be possible for companies to do such work internally, rather than going outside or helping them without paying huge fees to consultants, because this is the way.
I completely agree with you, and this is why we started working on this concept of a GraphAware knowledge platform, because the big issue with, famous companies like IBM Watson, for example, or this type of stuff, is that they offer this type of service as a service. So you need to let them access to all your data set, and then they will provide services to you. The knowledge platform, works in a different ways, because the idea is that you can install it on-premise and use it on your own infrastructure. You can also take all your data in your closed environment without accessing anywhere, so you can easily process all your email without having to share this email with no one, and then start processing from here. And this is a great advantage compared with other solutions in which you have to, okay, send your data and then you will get results. This is completely different. So this is the factor that, where we are working on in terms of providing services to the customer in a completely different way, where they have, okay, this is the software you can install on your machines and then make analysis of your data in a way in which no one else could access your data or get the results back and see what is happening on your data. So if you like, and obviously it is it can be easily extended because since it can be easily customized. can be, extended with a new relationship between data that are not, part of the NLP, for example, but are added later on as a manual task or even as an automatic machine learning task that could just create new relationship and store this relationship, increasing the knowledge that you have about your data as the beginning. So this is the idea of the graph, of the knowledge graph, and the way in which we are trying to apply to this sort of knowledge platform where you can easily manage your data, adding your own, process your own, add external tools that just as a, simple process and then add new information. Let me give you an example. You can even process images if you want. So you can even take the attachment of the email sent to this external system or even install it locally, get the data about the image that could be, okay, there is a tree, a car, a cat, or whatever else, and store this information again back in the knowledge graph. You can do this. It's simple. It's just a matter of some few lines of code. That's all. For example, we are already integrated with the ConceptNet 5 easily in a way for creating, a way in which we can get concept for simple tags, for example. But we can easily integrate Alchemy API. That is the next one in the list. And for example, in that case, processing image could be possible. Obviously, in this case, you should allow this image to travel along the internet, obviously. But there are a lot of tools that allow to process image in local without having to move them outside. But it's a matter of integration now. Once you integrate it, you store data in the knowledge graph, that's all. You can start navigating it and then build other machine learning on top of this new information that you gather in this way.